All right. How are we doing today, Milena?
Doing doing good. How are you doing?
I'm doing well. So, like the rest of us, looks like maybe you're working out of your house. Is that something that you're doing all the time? Do you travel a bunch? What do we do?
So mostly working from home, supporting our clients, but slowly but surely we're starting to travel again.
Excellent. Yes, I got to travel this week and last week it was travel locally. It was really nice to see people in person. So I agree with that one for sure. Looking forward. I got a couple more visits next week, so I'm with you. Um, well, as we get into this, we're going to talk about a study that your company has done and some of the ways that you've done it and what the results were. But before we do, I always want to get to know my guests a little bit better. And what I would love to know is if you could tell me about a book that you've either read recently or maybe you're in the process of reading right now.
So the last book I finished is called A Storm in a Teacup, and it's written by physicist, and it just tries to explain the most fundamental laws of physics with you know normal, common day, things that, everybody can relate to.
Hmm.
So it was pretty cool. So from magnetic fields and how pretty much everything is affected by magnetic fields and electricity to waves and things like that. So it was good because it's, coming from engineering, I could relate to, yeah, sure, we learn all those things in school, but how you can explain that to somebody else relating to, day-to-day things that we can all relate to.
So a storm in a teacup.
Yep.
All right, that's interesting. I've never heard of that one. I've been doing this a little bit now, this question, and I'm getting all kinds of interesting books. So I just
Very cool.
I had heard of one maybe a month ago, and I'd never seen it. So I just I'm about halfway through. It's called Bottle of Lies, and it's all about the history of the generic drug makers and the industry,
Oh,
and it does a lot of just sort of the history of maybe the FDA and how it came into being and why it came into being and what it did. And it's pretty interesting. It's certainly better than reading it off of the FDA's website. So I just put that up on LinkedIn today, and I think it's an interesting book. So so are you a book reader or do you listen to books?
I read.
Oh, good for you. Good for you. I feel like I fall asleep when I read. So
Well, that's the reason I read, to fall asleep.
yeah, there you go.
But I read a lot.
So do you have
Yeah.
a stack of unfinished books next
Uh,
to you?
oh, no, no. Whatever book I start, I always finish.
Ah, good for you. I always feel like
But
the first two chapters and I'm done.
uh,
Uh, those are always the best chapters. All right, awesome. Well, hey, so we're going to talk about this study that you guys have done at BioProcess Institute on diaphragm valves today. So as we get to do that, I just want to learn a little bit more about what you guys are doing. So I've heard you guys described, maybe self-described as the consumer reports of the pharma manufacturing space. So you're not doing vacuum cleaners or, Honda Accords or something like that. You're figuring out what's going on in the pharmaceutical space and what do we need to know about it. So can you share a little bit more about what it is that you guys do? Maybe this and maybe anything else that you guys do as a company?
sure. So the BioProcess Institute is a consulting, testing, and training facility. So it started about 12 years ago and was founded by Jim Vogel. And Jim has over 35 years of experience in the biopharmaceutical industry, working for a number of the big end users in the industry, most recently for Amgen. And I guess out of that experience came kind of a need to um, provide answers to things that end users didn't have answers. Um, Jim has also been involved in a lot of the um, standards development, like ASME BPE, and that's where him and I met each other. Um, many years back, and I had been involved in ASME BPE in my previous job as a manufacturer of components for bioprocessing. And we kind of shared that same feeling that there's so many unanswered questions and some of the things that we use, some that are very simple components that we don't even look at it much, and that could be the thing that can be taking down your entire process. And so that's how I got started working with him too, and that's the fundamental of the company, is trying to answer those questions by the means of consulting directly with a specific client. That could be an end user, it could be a manufacturer.
Mm-hmm.
We're creating kind of this bridge of understanding in between manufacturers and end users. And second could be just by doing training sessions. And the third one, which is what we're going to talk about, is, well, we kind of know what are the unanswered questions in our industry. Why don't we go and do some performance testing and trying to get those answers that can be shared, by, different people, and they can get the benefit of that information.
Mm-hmm. Okay. So today we're going to talk about one of those things, which is the work you guys have done on diaphragm valves. So can you start this by sort of telling us why you chose a diaphragm valve? I mean, there's plenty of like sexier things in the industry to study, right? Diaphragm valves are kind of everywhere, and they're maybe boring. I don't know. Maybe you're really into them, but you guys did this. So what was the reason behind choosing that to do the study on?
So yes, and that's interesting that you said that they're not the sexier things out there, and you may think of them as, well, it's also not the most expensive thing out there, and but they can completely take your entire process down and create a contamination issue when they fail. Mm-hmm. And there may be humble components, right? But they are, because the diaphragm is sealing your process. So that is what's creating the integrity of your process and maintaining a closed system, and not just diaphragms, gaskets do the same things. And
yep.
And so when they fail, is the system integrity what is at stake. And you can lose an entire batch, you can have a contamination issue, and this little component that may have been, maybe a few $100s to replace it, may now be costing an investigation that is over $1 million.
Mm-hmm. Yeah, so, the littlest thing can have a far-reaching, large effect.
Right. In fact, in many of these contamination investigations, the two, main suspects that are usually in the board, as people are discussing potential root cause, are going to be gaskets or diaphragms.
Mm-hmm. Interesting. All right. Well, I mean, I guess that makes sense. It doesn't need to be the giant thing. It can be the thing that is the most of. So I like that. All right. So just so that we're all on the same page, and we, again, we have a lot of younger people that seem to listen in on the podcast. So could we just start off with talking about what it is that a diaphragm valve is and how does it work? And we're gonna have you share the screen here to sort of look through a couple of these things. So why don't you walk us through the whole system here?
Sure. So what we have here is a couple of diaphragm valves, and there are three main components. We have the valve body, so that's what is in your piping system, and it will be either welded or it will be, clamped with a hygienic union. Exactly. The sandwich here in between is the diaphragm, and this is what creates that feeling to the environment, and it's also what makes the valve actually open and close. And then we have the actuator, which basically the function is to move that diaphragm up and down, which we can probably see better on the next slide. So here again, that was that body, that gray thing here. This is the diaphragm, and here's the actuator. So this actuator moves up and down. So when it moves down, this diaphragm ends up against this, that we call it the weir, That's what they're called, weir style diaphragms. So if you have fluid coming this way, this will come down and close it. So now the valve is closed. And then when the actuator moves up, then it releases that pressure, and then the fluid can go across the valve. So it's an on-off type valve. And again, we're talking, this is where your process is. So your process is touching the inside of that valve body, and it's touching the diaphragm. But it's not touching the actuator. And so this diaphragm's got two functions here. It's closing and opening, so it's letting the flow through or stopping it, but it's also sealing here so that, from the environment, so nothing would come in or out, of what is inside that piping system.
Okay, so for somebody that's listening right now, this is a difficult, and you don't want to know what we're talking about, this is a difficult thing to put in your brain. But so I would encourage, if you are listening and you want to understand this a little bit better, to go either onto YouTube and watch this, or check out the notes on the show. But just a couple quick questions just to get clarity. So we have this gap that's created between the weir and the diaphragm, which is where the fluid flows through. And then above the diaphragm is where the actuator is. Now, that space in and around the actuator, inside the head of the actuator, is there stuff in there, or is that all just air, or what's in that space?
Well, there would be springs that keep the tension on it, and a piston that is usually that you activate it with air. So when air goes into the actuator, it pushes that piston down, and then when you release the air, the spring was just the other way around. So the spring keeps the pressure, and when you put the air, it moves the piston up. So there's two ways you can have normally closed or normally open. But all of the mechanism inside this is not in contact with the process. So it is sealed actually by the same diaphragm. So the diaphragm does all of the sealing that needs to happen in that little system, let's say.
Okay, and then as the actuator sort of moves back up, the diaphragm follows it, and is that just by nature of the pressure of the fluid flowing through that pushes it up, or is there some kind of tension built in that allows it to spring up?
So when you have what we call a normally closed valve, a spring keeps the tension on the piston to keep this closed. So that's what is called normally closed. And then you need energy to make it open. So typically you let air into the actuator somewhere here, that, just the pneumatic pressure is going to push that piston up.
Yep.
And that's what's going to make this diaphragm go up. So the piston is on the back of the diaphragm, it's going to be attached to it mechanically.
Okay. So it is mechanically attached to the diaphragm itself.
Exactly. So when these two guys are, let's say, imagine glued together, they're actually kind of screwed. There's like a little stuff typically in there. So when this guy moves up, the diaphragm moves up. When this guy moves down, the diaphragm moves down. So it depends on a normally closed valve. Is a spring that keeps tension down. On a normally open valve, that means that you have to do something to close it. Actually, is the other way around. So you are going to need air to push the piston down to close it. And when you remove the air, it will just relax back to the open position. But the most common is typically the normally closed. The spring is always keeping it shut. And when you actuate it, because you put air to push this piston here, it will go up against the spring force and would open the valve.
All right. Awesome. Hey, I'm going to skip ahead and just ask a question, because I don't think this is one of the items that we cover later on. But if it's a normally opened or a normally closed, is one of them more likely to fail than the other? A normally open or a normally closed?
It depends on the application.
Okay.
So, and it depends also on the cycling, how many, they may be normally one way or the other, but you may be cycling them, multiple times through whatever you're doing, through open and closing.
Yep.
And but sometimes things that are closed a lot of the time may just have different issues that things that are open most of the time. So they could be a difference. Yes.
All right. It depends. It depends. That's a pretty good answer for most of these things. So, all right. So we'll back off of this visual for now, but, so one of the things I'm curious about is, what are the things that the users are going to care about with these valves? Obviously they want to know that they work, right? They want them to either stop fluid or allow fluid, right? As the case may be. And I'm sure as always with most things, how much something costs is always a big deal. Maybe how they fit into the facility, like a form factor. Some might have a huge body, some might have a smaller body. So what are some of the other big things that a user is going to care about with these?
Well, obviously the one that you mentioned first is do they work? and that's definitely number one. And what do we mean by work, right? Well, does it close when I want it closed? And can I, or also, does it leak through the shell? And they have things ripping out of the system, and so those are kind of the fundamentals. The second one is more on the regulatory. Does it have the right pedigree to be used in bioprocess? Are the materials of construction okay? Do they have the proper biocompatibility? So in this sense, now we're not just talking about stainless steel, right? We're also talking about a polymer. That diaphragm in there is definitely not stainless steel, as we obviously saw. It has to be flexible, right? So it's typically an elastomer. It can be what we call a thermoset or a thermoplastic. So it could be materials like EPDM, PTFE, other things. And those have to have the proper biocompatibility to be okay to use in biopharma. So that would be the second one. So that, without that, you can't even put it in service. So if you don't have that biocompatibility, USB 88 class 6, for example, don't even look at it. And so that would be the second one. For the most, these valves are kind of the standard of what people use in processing, in bioprocessing. So you can find thousands of them in each facility that you go, from water systems and clean steam all the way to fill and finish.
Okay.
So they have a very broad range of applications. Few exceptions would be where perhaps the pressures need to be really high, and so that may just be outside of maybe in some parts of the steam generation system where you may need some different type of valves. Okay.
So obviously you guys did this testing. Is there some sort of industry standard to test this equipment against? So all these there's a lot of different manufacturers. I think you worked with a few of them, probably the big ones. So did they have like an industry standard that they have to test their either diaphragms or actuators or the whole thing against to sort of prove that they're okay for the space? Or is it even more generic than that? Like maybe not pharma, maybe it's other applications as well.
Right. So it's more of the later. So there are different standards to perform tests on valves, just to mostly from the point of view of safety, that the valve's not going to leak, it's going to be able to seal, and it's not going to leak. Those are the two main things that we see other standards dealing with. And most of the manufacturers out there will have testing done according to those standards. Specific to biopharma, the ASME BPE has an appendix. It's a non-mandatory appendix K that is more of a accelerated or simulated bioprocess conditions. So basically we're simulating SIP cycles and then just making sure that the valve still function as as intended after, let's say, 50, 100, 500 SIP cycles. That is the only test that we're aware of that is specific to the intended use in biopharma. Where really one of the challenges in our industry is the thermal cycling. Many industries don't have that, but because we have to steam things, we get to make things really hot, and then they have to cool down, and then maybe through the process they're working at ambient temperature, and then you have to steam them. So is that change in the temperature that creates a lot of the stresses and issues? So that is somewhat unique in our industry. And this test, Appendix K, is basically, it's the base of how we did our study. And we, through our involvement in BPE, we have contributed to the development of that appendix. But it is not mandated. So you, as a manufacturer, as a valve manufacturer, you're not obligated to do that test. Nonetheless, quite a few manufacturers follow it, or they have started to follow it. So it's becoming more popular, let's say.
Okay. All right. So as you were just saying, this BPE is Appendix K. That's, you sort of use that as your baseline to do your testing. So could you sort of show us what you did to set up your test? What were the variables? What were the different products, things like that? And, sort of how you would perform your analysis in a scientific manner to get valid results. I think.
Sure. So let's see if we can share that.
The test matrix, I think, is what I'd seen.
Yes. Just have to find the share button again.
I didn't get rid of it, I swear.
No, you not. I just hit it.
There it is, like a pro.
There we go. So, right. So, besides just the test, when we decide to do something like a consumer report, the first thing we have to figure out is, well, who do we want to test? So, through our experience in the industry and through surveys, and we determine, okay, who are the people that are, the more kind of popular out there, but also who are the people that are coming with something that seems new or perhaps, sounds like could be better. So why don't we give those a try? Okay. And also what materials and what sizes. So that's how you get your permutations. So what we ended up with was a ballpark of 160 diaphragms that were tested. Two of the most common materials that are used, 82 were EPDM, 78 were PTFE. And then we picked what we call the primary size. So where we're going to do most of the experiments so that they're comparable, and then which was a 1 inch. And then we have a subset of other sizes just to see how much these depart from the behavior of the primary size. That's how we do different permutations that way. And then we selected some OEM manufacturers for each one of those, and also the aftermarket replacement diaphragms that are available.
Okay.
So that was, let's say, how we got started.
So again, if you're on the podcast, you can't really see this, but we're sort of looking at a graphic. It's a test matrix, and it starts on the left, this many diaphragms, 160, and then broken out in half with 82 EPDM. Of all different sizes, and then 78 PTFE, all different sizes. And then each of those are broken out to OEM manufacturers like Gamu and ITT and Saunders, and then aftermarket like Diaphragm Direct and James Walter and Newman. So you have sort of this tree that's going out to try to get a broad spectrum of diaphragms from across the industry. Okay, so that's the test matrix, and then you had like these different exposure conditions. Right. You had them exposed to.
So again, the test is mostly based on ASM EBP Appendix K, which is steam cycling, and until recently was also combined SIP and CIP cycling. So the cycles, how long and what temperature and what chemicals and what concentration that's basically given by the appendix. But so we base it that way, but we had some other milestones too. So there were some valves we just tested to 100 SIPs, and then we looked at them. Some we went all the way to 500 SIPs. So there are certain things that you cannot be disassembling all the time to try to check. So you kind of need to pick a few that you're going to be testing earlier on, because if you get to the 500 SIPs and they're all, done, you really don't know when they fail, right? So we need those kind of in between milestones to figure out where did they fail. So all I know now is that by 100 it's all bad, right? So that's why we have these different.
So it gives you sort of a bracket and a sort of a sanity check on the test to make sure you're not wasting your time on a whole bunch of other ones then, essentially, right?
Right.
Yeah, but since you can't have like a little micro machine man inside with a camera looking at it during all these processes, this is the only way to do that.
Right. Yes. And then we, besides just the straight SIP, we had different combined SIP with CIP cycles. And we compared that information to also the ones that were only to SIP, see what trend we could see with that. Aside from that, we did another one that we consider was very important for the industry, which is only in contact with turbulent hot water. So you would know an application probably with water that is like hot. Right. So
I've seen it a couple times.
Right. So that's our typical, hot Wi-Fi loop. And those valves, because it's a self-sanitizing system, they're usually not steamed. They don't see SIP cycles. So we wanted to answer that of, are there problems with a certain material or valve manufacturer that you shouldn't be using, or that is absolutely better and you should be using precisely in that kind of application? So in that case, what we did was just a constant 670 hours of recirculating water at a certain flow rate through those valves.
Was that like at 80 degrees C or 85 C, like a normal loop would be?
Exactly. And it was at least 5 feet per second that we all used to design these things. So, and then we had another was similar, but it was with static steam. So rather than being cycling, you heat up, you cool down, heat up, just to keep the steam there for 670 hours to see what happens to the diaphragms.
So that would be more like a deadheaded scenario, or steam flowing past it for 670 hours.
This was a deadheaded scenario.
Okay.
And then we have finally a separate chemical exposure test, where rather than just looking at what happens with CIP cycles, we just look at is the diaphragm going to dissolve if we put it into a caustic solution or phosphoric acid, and then they stay in there. This is actually according to an ASTM standard to check for chemical compatibility, and so that got us another set of results.
Okay. All right. Well, it's a lot of different kinds of tests there for get some good information. And now you have this is like your racetrack slide.
Right, exactly. So what we're saying is that, if you think of a racetrack, that's what we do with these valves. So they go into this our little SIP skid, and then they are continuously exposed to the cycles. And then we have certain milestones where it's like the pit stops, right? Where, okay, we're going to take some of them and see how they're doing and whatever. Some may continue. Some, if we want to disassemble it, do every, possible analysis, that may be just to where they stop. So we started with 160 diaphragms here. We had 11 that we did 50 SIP cycles, 50 CIP cycles. Then we had 40 that we got to 100 SIPs. And then we continue, all the way. The majority were tested all the way to the 61 SIP cycles. And besides, we have the ones that we had the chemical exposure or the hot water exposure, steam exposure. And at the end, we had 156 diaphragms. So there were 4 that didn't even make it through the get-go.
Okay.
So that's the difference. So you can find that. You install it, you put that diaphragm and everything, and it didn't seal from the very beginning. So there's no point of continuing the test at that point.
Mm-hmm.
So it can be another drop here, right in the just you're gonna start your race car at the race,
and basically you're just pulling off to the pit stop as they go. Yeah.
Right.
And you're like, hey, you're done racing. I got to change your tires and check on you. So as you go through, how many were these fully assembled diaphragm valves, or were they just the diaphragm themselves? What was it different depending on the test? So like your chemical exposure, was that just the diaphragm sitting in a bucket of chemicals, or was it like the full system, the full like diaphragm valve setup with like the chemical sort of injected in there and held for 670 hours?
Right. So in all cases, except the chemical exposure, was the assembled valve. So we had valves from all of the different manufacturers and put the diaphragms in there, follow their assembly instructions. The only exception was with the chemical exposure, was just basically the diaphragm itself was submerged in the whatever solvent we were using and left there for 670 hours. So that's the only one that wasn't the complete valve.
Okay. I'm interested, like, from one manufacturer to the next, if they all say they're EBDM, I mean, I would think that they would all come out exactly the same, right?
Oh, not at all. Not at all.
Interesting. Very interesting.
They are very different. EPDM actually just means it's the type of elastomer that you're using. It doesn't even mean a specific composition.
Right. So that's something for people to understand, because generically speaking, you just sort of specify EPDM, right? You don't necessarily specify a very specific kind or whatever, right? It's
yes,
EPDM.
And for sure this test, and even just the chemical exposure, will show you that EPDM from valve manufacturer A and EPDM from valve manufacturer B perform very differently. And not just because on the chemical, you don't really have the valve in the mix. And you will see that the materials just react differently to the exposure. And that is part of what becomes part of the performance, that the difference in performance that we see.
Oh,
they're not all created equal.
Apparently. All right. So I think you have one more that I was interested in seeing. Oh yeah, here you go. So these are the things that you're actually measuring, right?
Right. So once it is how we do the test. So we saw the racetrack, and now what are we going to look for once we do the test? So we just look at it and throw it away. So these are the things that we do to evaluate that performance. Number one is sealability, and do we have pneumatic integrity? So that means that seal, what the valve is closing, that's what we call the seat, the weir. So can we actually close it, and then we don't see any liquid coming, downstream or air in this case, because it's a pneumatic test that is, zipping through. And then we have also integrity on the shell. So this is at the end, the end here at the border of the diaphragm where it's sealing, sandwiched together, with the valve body and the actuator. And we don't want anything leaking to the outside. And so that is the shell integrity. So we don't want to see things that are leaking. And here it's kind of you can see like a bubble coming out of a valve that it was supposed to be in the closed position.
Yep.
And those integrity tests can be done with air, or they can be done with water. So that's the first thing. This is what we call, if you fail any of these, you don't have the basics at that point.
So this is the does it work? This is the does it work?
It does it work question.
Right. So like if you're actuator isn't working correctly, independent of your diaphragm, there's a pretty good chance it's not going to be closing or opening the way it needs to, right? So, so we have how well is it actually actuating and creating that, and then it has, how well is the body squeezing down on the diaphragm itself and keeping any of the fluids from getting out, or potentially, I guess, getting something in. That would be interesting. And then how well does it like sit on the weir and stop fluid from moving from one side to the next.
Right. So usually when you have a sealability problem, it's game over.
Yeah.
And then this is, okay, does it work? And this one is more like, does it really work? And that's what we call entrapment. Entrapment risk is actually when your sealing in the diaphragm, you can probably see it better in this one, is on this edge here. And you can see that from that edge where it's supposed to seal to where the holes are, where you have your bolts that are sandwiching that diaphragm together, there's quite a lot of room, right? So let's say this seal is not working very well, and like here, we just put some soiling media through and obviously made it through it. But this is not necessarily going to come out that you can see it as an integrity shell problem.
Right.
The valve is not leaking, but it's trapping stuff there in between. And when that valve opens and closes, there is a potential, the same way that stuff went there, that stuff can come out and contaminate your next batch. So entrapment is a real problem because you don't see it. So if that's still lurking in the dark, waiting to contaminate your process.
It's not evident. It's not evident.
Correct. Right. So so in most cases, failing entrapment, so if you're already getting things in there, then it's also like it's game over. And knowing when that may start happening, it can really save a lot of contamination from happening. The other problem with that is also for the same reason. Once it's in there, it's kind of trapped, right? So that's what we call it, entrapment. So you can't clean that. You can CIP that valve until the cows come home, as we say in Wisconsin, and it would still not clean that.
So this inspection picture, again, somebody listening can't tell, but she's got this picture of this opened up diaphragm valve, and you did like the CSI blacklight on this to show, like a luminescent, like where it had failed, where some soil or something had gotten beyond that knife edge there. So like, is that what people do on site? I mean, do they open it when they change diaphragms on some basis and they're inspecting? Do they do that, or do they just open it up and look at it and it looks clean to me? So could you share what that looks like at a site?
Yeah, so it would depend on what the soil is. Some people can actually see product that was left in there, but by the time you take it apart and figure that out, your problem already happened, right? So it's been there probably for a while. And at that point, people are going to replace the diaphragm because they have disassembled the valve anyway. So the way we do it, so in the case of on-site, it depends on what your media is and whether you'll be able to see it or not. What if it's a water valve? I mean, you just seen Wi-Fi, for example. I doubt that you're going to see, once that evaporates, what are you going to see? You don't see anything. But that doesn't mean that something could have not got entrapped. So what we do in this test is basically it's a soiling media, and it's a fluorescent media. And we just basically run it through the line and at a certain pressure for a whole hour. And so once we're done, then we just let it dry. So it's soluble in water. So we just run it, it's like you have a dye in a bucket of water. So that's basically what we're doing. We're passing that dye through it. And then once it dries out, what is left is that fluorescent residual. So if the water was able to make it through any of those, those sealing points, the fluorescent residue there is going to stay there. That's not going to evaporate. And then with a UV light, we're able to see it.
Okay. All right. I keep knocking you off your game. So last one is this visual
Yeah.
condition.
Right. So visual can also be important. There's different degrees of how bad a visual condition is. So you can have things so extreme, like this diaphragm has a cut through it. So that's a problem. Obviously, now you are not maintaining any integrity.
A hole in your diaphragm, not good.
A hole in, not good under any circumstances.
Write that one down. Write that one down. Got it.
Well, there are some things that may not be as dramatic, and sometimes people panic. It may just be discoloration. That doesn't necessarily mean that anything bad happened.
Okay.
So more grays, it's not black and white. With visual condition, more grays in there, while with sealability, it's black and white. It seals or it doesn't seal. And entrapment is close to almost the black and white, unless for whatever reason you have an application where you say, I don't really care.
Mm-hmm. Are there established criteria for this space, like that this is a black and white issue, or is it really just like a judgment thing? I mean, again, if it's leaking, that seems pretty easy to determine as a problem, or if it's got a hole in it, right? That seems easy, but is there like a regulatory type criteria that people would follow for that?
Well, there is, but it requires interpretation, right? Because the FDA tells you you cannot have anything that would adulterate the process or the drug product or the process to make it. And so then you have to interpret that to that visual condition. I mean, maybe what I have after using, let's say, an EPDM diaphragm is some black residue because it kind of was glued into the stainless steel, and it's quite a lot of it. Where does that go? That goes somewhere. Does it go into your product? It can. So, or you have a way to mitigate that later on the process. So those are the judgment calls that people will need to do. But ASME BPE gives some criteria about visual condition that is acceptable or not. And we at the BioProcess Institute created a modified one that would look into a little bit more detail of what BPE is recommending.
Okay.
But again, it always has to be understood in terms of what your application is.
Mm-hmm. Well, and that makes sense. I mean, what BPE says sort of turns into a little bit of a gospel, right? And then it's kind of a rule. What you say is helpful to better understand it rather than just now everybody has to do a certain thing. All right, awesome. So I think there was one more that I wanted to see. It was, what's your next one here? This one. All right. So this is like, how do you, okay, so sealability is important. Is sealability more important than, one of the other things? So like, how do you actually weight that stuff to determine a score for these guys, right?
Right, exactly. So there were two things on that we did. Originally, what we created was kind of a scorecard for each diaphragm, so that then you can compare scores. So then somebody's going to end up with a better score than the other guy, and then that's how you would determine, okay, these guys are probably better. And then we also did an analysis that was just based on failure rates. But on this one, which is with the purpose of comparing different manufacturers, we gave some weight to those potential failures, saying that integrity is by far the most important thing. The seat, pneumatic seat, pneumatic shell, and hydraulic seat integrity. The scores in there, okay, does it work, right? Definitely. The valve's not leaking. So we gave that a lot more weight than the other things. Even entrapment, we gave it significant weight, but entrapment, when we looked at the data, there's going to be some trends on how that is also related to shell integrity.
Right. So it's not just one or the other. Yeah.
Everybody has shell integrity, has entrapment.
Mm-hmm.
But not everybody has entrapment, has shell integrity. So sometimes you don't see it. And then the visual, we gave it a certain percentage as well. So what that allows us to do is that for each single manufacturer and material, we can create a chart like this, where we have a score from, the best score is 10, and then based on that, so each one of these, it would get us its own score from 1 to 10. Some are just basically, it's going to be all or nothing.
Yep.
Some have more grade in between, like the visual, you can get a score of 5 or maybe 7. And then that multiplied by that weight that we gave each one of them is what creates these graphics and the overall score. So this particular material manufacturer had this 8 point something score when it got to 100 SIP cycles.
Mm-hmm.
So by the time it made it to 500 SIP cycles, it was maybe like 7.2, something like that. And
so the score is independent of the test. The score is its own thing. And then almost like don't even look at what the test was. Just look at the valve or the diaphragm, score it, and then it goes back, whatever test it was is what it was.
Yeah, so the idea is more that if I have manufacturer A, I want to compare to manufacturer B. If manufacturer B has these bars are higher, then they're better. But compared to the same exposure, right?
Yeah.
So I want to see if it's better, was it 100 SIPs or was it 500 SIPs?
But technically though, if you had 100 SIP or 500 SIP, in theory, you would always expect the score to be lower on the 500 SIP than the 100 SIP, right?
That is correct.
Okay.
Yes.
All right. Awesome.
All right. I think that was...
That's really good. So this is how you get in your consumer reports, the red circle with the little white dot, or the half black, circle that Consumer Reports does. This is the BioProcess Institute version of these things. So
that's correct.
So this is how you did it. So, all right. So for those that are listening or watching or whatever right now, we're not going to tell you who won. That's not what's going to happen here. But if you want to know who won, you're going to have to follow up with Milena after this interview. But what kind of results did we get? I mean, again, I think we talked when I mentioned the idea of EPDM being EPDM, and you said, no, not really. It seems like a Ford Chevy thing when I visit a lot of places. Oh, we use these guys. Yeah. Some people swear by them. Some people swear by this one company, and other place swears by a totally different one, and they both hate the other one. Is there really a big difference? So when you look at these results, how wide of a difference did we see?
Yes. So the kind of results that you're going to see is you can see their manufacturers that fall in, this is like, from unacceptable to an acceptable score in sealability, entrapment, and visual conditions. You would see that there is a range. So some people do a lot better, but there's always the one that didn't do that well. Mm-hmm. And sealability is the same, where most of the people were okay for the longest time. Entrapment starts to divide the good ones and the bad ones, and you see a lot more people that fall kind of in the middle range, and a lot less that are still in the green area. And now you get some pretty bad boys here in the unacceptable. And same thing with the visual conditions. There is much more granularity there. And you can see, for example, with EPDN, we have quite a few that fall into the unacceptable, with a lot of EPDN left on the weird, or sometimes we see things like that you kind of need somebody really strong to remove that diaphragm from the valve body.
Yeah. So again, if you're listening to this, we just got basically a bar graph kind of visual of these different categories: sealability, entrapment, and then the visual condition, from the low end of red and unacceptable up to the green, and you get quite a bit of variety there. And then you have more of the, you know, this what's this next one? This is a failure.
Yeah. So related to, did I jump ahead?
Well, you're at the results of the study failure chart. So you got brand A through brand F.
Right. Mm-hmm. So this is like, we're just looking at the percentage of failures. These are only what we call the big failures. These are the integrity and entrapment failures.
Okay.
So it's not even considering the visual and how you want to interpret
These
that.
are game over failures. These aren't, oh, it would be nice if it was prettier.
Yeah. These are the game over failures. And even on those, we can see that we have some brands that this is at the end. This was actually through all of the different exposures. The hot water, the static steam, the 500 SIPs, the 100 SIPs, the combined CIP, SIPs, and all of the different ones that we did. We had some brands that never had any of the big failures all through the test. And
okay, so I just want to make sure I understand this. So again, we keep this generic. So we're talking on this one about material. So this is material A. So we don't know if this is EPDM or PTFE, right?
That's right.
But it is one of those two materials, and you have 6 different brands using that material, whether it's the name brand like GAMU ITT, or if it's the I'm blanking on the word I'm looking for, but like, you know, your replacement diaphragms from lesser known brands, let's just say. And how often or what percentage of the tests did they fail? You had all these different tests, and what percentage of those tests did they at least ultimately fail?
That's correct. That's correct. And then we have a range that people that didn't fail any to brand F that failed 67%. So
2/3 of the tests were failed by one of these brands.
Exactly.
Wow. That's not a good record.
So that's they're definitely not all created equal, even if it was the same type material.
Mm-hmm. Yeah, that's a pretty big change. So when you used I'm struggling here with the word for whatever reason, you know, the replacement parts. Mm-hmm. This is did you put those into one of the name brand valve bodies?
Yes, that's correct.
That's how you did it.
Go into a specific valve, whether it's an ITT or GAMU or Saunders. That's what they're intended for. Yes.
Okay. All right.
So what we call replacement diaphragms, they don't make the valve; they just make the diaphragms.
Right. Okay. I'm trying to think. Was there another one that went with this? I think that was it.
This one is actually an interesting one. It's a spider web. Kind of hard to describe, but in this, basically, if you look from the center to the outside, is the number of SIP cycles.
Okay.
On each one of these lines of different colors is one of the different failure modes. So the blue is the seat integrity, the orange is a shell integrity, the gray is entrapment, and the yellow is visual. So on each corner, it looks like an octagon, or well, something like more than an octagon. It's got more than that. Is each brand. So when all of the dots on that brand are right on the 500 SIPs, which was the max that we tested for, that means that it made it basically all the way to 500 SIPs without any issues with seat, shell, entrapment, or visual. And here we have one that...
The brand A is all of them.
Yeah, for example. So it must have been the one that we had the 0 in the other graphic. That's the one, probably the one. But you can see that in some of them, that's not the case. So if I wanted to know, for example, let's see, brand C. And brand C says that up to 500 SIPs, they were okay with the seat. A little not so okay with the shell. So maybe I want to replace this valve this diaphragm before I get to 500 SIPs. But actually by 400 SIPs, we already could see entrapment issues. And if I really care about the visual, by 350 SIPs, they were already having some significant visual issues. So this may be a brand that I may want to replace. Yeah, something between 300 and 350 SIPs. So we think this is a great way for people not to waste their time replacing diaphragms too soon or too late. But the point here is that there is no recipe that you can use for all the brands and whatever material. This is dependent on the material and dependent on the brand.
So I had another podcast on maintenance 4.0 and in relation to Pharma 4.0 and sort of applying science and data to how you maintain your facility and how you take care of your equipment. And I think, one of it sounds great. Everybody would love to do that kind of stuff. And at the end of the day, it's like, but how do I do that? You need data and results before you can come up with the right amount of cycles before you have to change something or inspect something or whatever. So what you've done here is you've put together a composite for all of these different things to go, hey, well, this isn't perfect and there's other variables we don't know, but this seems like a really good starting point to base some of that off of, rather than just saying every year, right? Or every 6 months or every 1,000 cycles or whatever random thing that you decide to pick that may or may not be based on anything in reality.
That's right. And I think that was the inspiration of all the work that we've been doing, was exactly that, so that we can, if every facility would need to develop the data to come up with this chart, it's hundreds of thousands of dollars each one. And so we thought that there was a lot of collaboration just by trying to, put what people use the most and give them the basics of it. So something that we've done a lot is that out of this data that we have in the study, we can do bridge studies for specific clients that may say, hey, this is great, but now my steam temperature is a little higher. How do I bridge that to this information? And then that's a study that doesn't cost as much as, doing the whole thing.
Right.
So that's where we see the value of, we're all kind of using the same brand and in very similar conditions. I mean, so that's the purpose of having more of a standardized test. And we've seen that people have been able to move from just time period preventive maintenance, like, okay, we're going to do a 6 month period, to more of a trend analysis. And based on, maybe it's not the time, but it's the number of SIP cycles. And then again, just exactly as you said, if you want to do that and not do it, well, I'm going to do it every 6 months because that's what we always do, then you need the data to support that. So, but you imagine somebody that is doing preventive maintenance, call it once a year. There aren't too many applications out there where you will see 500 SIP cycles in a year. Sometimes we already say that 100 is, quite a lot, maybe 100 in a year. Yeah, it's something that people see more often.
Right.
And so now imagine you're changing this brand A, that nothing happened to it, all the way to 500 cycles, and you're changing it every maybe less than 100 cycles because you're doing it on this, I have to do it every, once a year, all the diaphragms are replaced because we're not going to take any risk. Now, if you have this data to support it, you may just say, well, okay, no, we're not going to do it every year. We're going to do it every 2 years, 3 years, whatever, that you feel comfortable with your risk level. And that is an enormous amount of savings, not just on the diaphragms, but it's on the time that it takes to disassemble these valves and replace the diaphragms and put them back together.
So to that, I guess to that, what you've done on this study is it's been exposure cycles, temperatures, all these different things. Now it's tough to simulate number of years or time without actually taking that much time. Do you have a way of approximating if age has an effect on this beyond just the exposure itself for these materials? Like, so you might say, you know, this material without anything else is nothing's really going to change in any meaningful way for 10 years. But once you start exposing it, is there enough, you know, tiny degradation so that that's not really true anymore? And then, you know, the lifespan of the meaningful life of that polymer starts to become a problem. Does that make sense? I don't know if I asked a good question there.
Yeah, so the materials would have a certain shelf life.
Okay.
And that's obviously, you know, that's it's a different consideration to what we're doing here. But yes, if it's going to take you 20 years to do 500 SIP cycles, I'm pretty sure that diaphragm is not going to be any good, because the shelf life for most of these things is no more than 10 years.
Okay.
So yeah, you got to have that consideration as well, of course.
Okay. Yeah, I just didn't, I don't know if there's a way to approximate, you know, over time how that ultimately would, you know, okay, it's 10 years, but is it really, even though it passed all your 500 cycle tests, is it really more like 3 once you've done this, because it just starts to wear it down a little bit and you can't see that? Probably not an easy thing to measure.
No, I mean, some of these materials really don't degrade. Just like PTFE would have very little degradation over time. They tend to have very long shelf lives.
Okay.
But some elastomers, they usually, and most manufacturers will provide a shelf life for that diaphragm.
Mm-hmm.
So yeah, but it is in the years, and it's usually, yeah, it's in the neighborhood of 10 years. So
okay, that's a long time. All right, so this is great. So this study, this is something that somebody can buy a study so that it doesn't say brand A, brand B, right?
That's correct.
Anymore.
You'll find out who brand A is.
Yeah, you get the big reveal. The curtain will open up on this slide, and you can see who it actually is, right? So right. That's something that somebody could reach out to you and buy from you. What are some of the other ways you like help manufacturers with this information? Like, so to me, I'm looking like, oh, it sounds like we all should buy brand A, right? So I mean, it's not that simple. It's not that easy. But so what are some of the things that you do with manufacturers to help them with the stuff that you've learned?
Right. So as we were mentioning in the beginning, so we like half of our clients are actually end users and the other half are manufacturers. Mm-hmm. And so we've helped manufacturers to identify what was the weak link in their design. Where are they failing? Is it on the entrapment? Is it on something else? Or everything is great, but the visual condition, the EPDM is sticking to the metal or something like that. So once that's identified, then they know what direction they have to focus their efforts in, and also get some comparison to what the other guys, how are the other guys performing. Mm-hmm. So obviously nobody has the perfect valve. There's always going to be an application when one valve is going to be better than the other. Mm-hmm. And nobody has the perfect material. So it's all in comparison to what else is out there. So yes, so the report can be used on those in those two situations. For a manufacturer, you want to find out where are you standing and what are your weaknesses, so you can improve on that. And for the end users, certainly to know, so what is that I want to buy so that it's going to work, and how often do I have to replace it?
Okay. So as we sort of close this out, I just wanted to go through a couple of these things. So something that I thought was really neat about the presentation that you have here is you have these frequently answered questions instead of frequently asked questions. And they have to do with 3 different things, right? You have to do with the selection of like diaphragm materials or manufacturers. They have to do with the use of them, and then they have to do with predicting them, or predicting what is going to happen, beyond today. So, is this something that you walk through your clients with to try to sort of help them through, or is this just a page on your website?
No, that's actually our daily life, and yeah, it's helping people through this. It's quite real. So, unfortunately, in many cases, we don't get involved until it's already in use, or there was a failure that created a contamination, and are trying to help people identify the root cause and close their CAPAs, basically, corrections and corrective actions.
Mm-hmm.
And that being said, I mean, in general, diaphragm valves work. When you look at, there are great differences in between manufacturers and the materials, but in general terms, what we found is that by 500 SIPs, but only 3% of all of the valves that we tested, all the diaphragms, had a integrity issue.
Mm-hmm.
And about 17 had entrapment issues. So I think it's fair to say that the technology works, but this is under our control conditions, right? So we have the standardized tests. They are all going through the same racetrack. But that's not exactly the condition that people may be using them. So what we see sometimes is that by knowing what they're able to do, we're also able to tell when they had been abused. So if they were not installed properly, if they were torqued too much or too little. So those are situations that are outside the control of the manufacturer and go more into how should I use my valve. Mm-hmm. And with that, we also have some information in there on what should be your proper torque or the percent compression when you install that diaphragm. Do you need to retighten them after the initial SIP cycle or at some other milestones? Some of them, many of them you do, some you may not. And so knowing how to use them is just as important as selecting the right one.
Mm-hmm. Yeah, it was one of those pictures that you had, which showed entrapment. And when you see where all the material is along the flanges, it almost looks like, well, that looks like a bolt pattern issue, the way it came out. It almost looked like it all sort of went towards one of the bolts. So I was curious, you got to tighten them like you do a tire.
You do, yeah.
Yeah.
Yep.
Yeah. All right, cool. Well, hey, this was really good. We got to talk before this, I don't know, twice, I think. And it's very interesting. I think this is super useful information for anybody in this space. I can't imagine why this would be anything but helpful to somebody that has to take care of a facility that has, hundreds and thousands of these in your facility, especially on the bigger sites. But even on little sites, this is still just this thing that's always going to be maintained and always going to be changed. And it's moving parts, right? So it's such an important thing to have a good handle on. And if you can help predict what's going to be going on down in the future, then you can stave off potential issues and save batches potentially, right? That's like the worst possible thing. So I really like what this is. I'm hoping that we could do another one of these to talk about gaskets. I mean, everybody's favorite thing, I guess.
Sure.
I'm actually pretty interested to see what other stuff you guys are doing in the future, but this was really interesting. We sort of based this off a presentation that you shared. Is this something that's available online, or is this something that you sort of do with people live?
We do mostly live with people,
okay.
And if people would like more details, and there is maybe a condensed version of this in our website.
Okay, so yeah, so if you listen to this and maybe you're interested in it for your facility or Maybe you're a valve manufacturer. I would expect that most of them have probably heard about this already, so and probably keyed in on it. So you can look up Milena online, either on LinkedIn or go to their website. Both of these will be linked with the episode, so you can check it out there. But I'm really excited about this. I hope people really like what you have to say here, and I hope a whole bunch of them come and buy the report from you guys so that they can again pull this curtain back and see what is actually going on. So thank you so much for being on today, Milena. Really appreciate it. Look forward to talking to you again soon.
Well, thank you. Thanks for having me.